In this video, we'll define subspaces and look at an example. Let V be a vector space, and let W be a subset of V. Then W inherits most of the vector space properties of V. And we need only show the following three things to prove that W is a vector space. 1. It is closed under addition. 2. It is closed under scalar multiplication. 3. It contains the zero vector. If W satisfies these conditions, W is called a subspace of V. And subspaces are vector spaces. So in that previous video, when we wanted to show that the set of continuous functions was a vector space, what we were really doing was showing that it was a subspace of the space of all functions, and then using the fact that subspaces are vector spaces. These three conditions can be collapsed into one. W is a subspace if and only if it satisfies the following condition. If W1 and W2 belong to W, and K1 and K2 are any scalars, K1 W1 plus K2 W2 belongs to W. So this single condition gives you all of these. If we let K1 and K2 be the scalar 1, this becomes closure under addition. If we let one of these be 1 and the other be 0, this becomes closure under scalar multiplication. If we let both these k's be 0, this becomes the statement that the 0 vector belongs to W. Let's end this video with a quick example. Let's prove that the set of all differentiable functions defined on some common domain D is a vector space. And we'll do this by showing that it's a subspace. I mean, this set is a subset of the vector space of all functions. We'll demonstrate that it's not only a subset, but a subspace. And subspaces then are vector spaces. Two ways we could go about this. We could show each of these three conditions, or we could try to do it in a single blow with this alternative definition. Let's just use the first definition we gave. These are basic theorems of calculus. So this set needs to be closed under addition. That is to say, if F is differentiable and G is differentiable, we need F plus G to be differentiable. And that's practically the first derivative rule we learn in calculus. That if F and G have derivatives, then so does their sum. In fact, we have an explicit formula for this derivative, so it certainly exists. 2. We need closure under scalar multiplication. So if f is differentiable, we need k times f to be differentiable. And again, this is a very early rule that we learn in calculus. We have an explicit formula for the derivative of kf. It certainly is differentiable, and its derivative is this. Finally, we need the zero vector. Well, in this context, the zero vector is the constant function, f of x equals 0. And we need that to be in this set. We need this to be differentiable. And it certainly is. In fact, it has the property of being its own derivative. The derivative of any constant function exists and is the zero function. So the set of differentiable functions is a subset of a vector space. It satisfies the 3 subspace conditions. It's a subspace of that vector space. Therefore, it is itself a vector space. In this video, we've defined subspaces. In the next video, we'll show another example of a subspace.